Hi. In this third and last presentation of the regular sequential circuits playlist, we will discuss the specification of the first coursework assignment, a counter-based electronic dice. At the end of this presentation, I hope that you will be able to explain the functional requirements of this assignment using your own words and to plan the tasks needed to implement a solution using Vivado. The presentation comprises two parts, the first of which addresses the requirements for the e-dice. You will notice that this is a special e-dice since it supports a cheating mode whereby we can triple the probability of any one of the 6 possible results. The second part of the presentation will look into the tasks that you will have to carry out to implement your solution. Let's start by the requirements. This slide shows an overview of what you are being asked to develop. Our e-dice should support a cheat input to switch between normal and cheating modes, and 3 result selection inputs to indicate which result should have a triple probability when the cheating mode is active. The 2 position switches available in the basis 3 board can be used to drive the cheat input and the result selection inputs. Then we need a run input that will throw the dice when pressed and stop it from rolling when released. An onboard push button can be used for this purpose. The remaining inputs represented here are the usual clock and reset inputs. You are required to use 2 methods to show the result. One of the 7 segment digits and 7 LEDs, which may be laid out as shown here to represent the 7 dots in a dice. Well, you may of course use the onboard LEDs, it's just that they don't replicate the position of the dots. The functional requirements may be summarized as shown in this slide. The 3 result selection inputs will define what result has triple probability, except of course when the cheat input is at 0, in which case all the results are equally probable. The 3 result selection inputs allow you to specify 2 illegal combinations, since the result can never be 0 or 7. In such cases, you must make sure that all results are equally probable, even if the cheat input is active. The run button, as we said a while ago, will throw the dice when pressed and stop it from rolling when released. In this coursework assignment, you are being asked to use a binary up counter to implement the dice. Since the state diagram is predefined and just moves through the 8 possible output combinations, what we can do is to decode the appropriate output patterns for the LEDs and the 7-segment digit, considering that state 0 will output result 1, state 1 result 2, and so on until state 5 outputs result 6. At that point, according to the cheat input value, we will either let the counter continue and decode the result indicated by the 3 result selection switches, or reinitialize the counter to restart the loop. So what tasks are you required to do? To start with, I recommend you to try to draw a block diagram including a 3-bit counter with an enable input, use it to alternate between run and stop, and a synchronous clear input to reinitialize the loop or let the 2 additional cheat states happen. You also need the combinational decoding logic to drive the LEDs and the 7-segment digit. And you need, of course, the additional logic gates that will take the cheat inputs and the counter outputs and drive the synchronous clear input of the counter. When or once you are confident that your block diagram represents a working solution, you will be ready to start coding. You may wish to create or import a standard description for the 3-bit counter with enable and synchronous clear inputs, and to create the additional combinational logic represented in your diagram. Then you can use a top-level structural description to interconnect all these blocks. Once your top-level description synthesizes without errors, you are ready for design verification. You will need to create the simulation source file where you will include a number of representative operating conditions and to check that your solution works as expected. What would it take to carry out exhaustive design verification in this case? When you have proven the correctness of your solution, you may continue to implementation. You will have to create a constraint source file to specify which FPGA pins shall be connected to your eDICE inputs and outputs. But since you will be using the onboard resources, all you have to do is to edit the corresponding lines in the master constraints file provided by Digiland. And then you will finally be able to generate the bitstream file to program the FPGA and to try out your solution in the Basis 3 board. I wish you good luck with your work. Thanks for your attention.